All right, hi guys. We're doing 5.3, and this is really putting the two ideas together that we learned. So 4.10, we learned how to take antiderivatives. Now we haven't learned all the rules yet, but we learned the basics. Then in 5.1 and 5.2, we've been, building up towards the definite integral, right? The integral of a function. Now, those use the same symbol. Right? On purpose, right? Here's the connection that we're going to learn today. Okay, so just remember, so this is the, we're asking for the antiderivative, and then this guy, this is our integral, right? Now, um, both of these are integrals, right? One's indefinite integral, one's the definite integral. So maybe what a better word would be the net change, right? The net change in signed area. Okay. But we're gonna learn the connection. Let's learn the connection. So before we get there, let's talk about the mean value theorem for integrals. Okay, so we learned a mean value theorem earlier. What are we talking about with integrals? Well, what so happens to be true, and we've seen it a little bit with the examples we did in 5.2, is this. So first of all, we need the conditions. So if f is continuous on the interval a to b, then there is a c where c is in the interval, right? Those are less than or equal to signs, and the y value at c is equal to the average value of the entire function. Okay, so when we learned the average value formula last time, but it just so happens that this is actually always true. Okay, so I pointed it out on the examples we did where the average value was actually a y value in the interval, but this is actually always true. So it's kind of crazy. So let's go ahead and try to use this. Okay. If you want to see the proof, you can check out the textbook. It's pretty quick. So yeah, let's do it. So let's do an example. So let's look at f of x equals 8 minus 2x on the interval 0 to 4. Okay. So we're going to find the average value of f. Find, and then we're going to find x equals c, which is guaranteed by the MVT for integrals. Okay, so we're going to do both. Find the average value and then, solve this whole thing. Okay, so let's do it. First of all, let's get the actual integral here. Okay. So sometimes we abbreviate it FAVE, F average value. So that's going to be 1 over 4 minus 0, integral 0 to 4, 8 minus 2x dx. Okay. We got to get the integral. So what is this integral here? We're going to have to draw it. So we're going 0 to 4. So that's 2, 3, 1. There we go. And then y-intercept is 8, and we subtract 2 every time. So we'll go 6, 4, 2. So we got a point here, point here, point here. Whoops. Yeah, point here, point here. There we go. Okay, so it's just a triangle. The height is 8, the base is 4. So we have a quarter, and then the area of the triangle, a half times uh, base times height. Okay, so this is actually equal to 4 once everything settles down there with the algebra. Okay, that's just the average value. So that's the first part. Now we need to find, so we need to find C where f of c equals the average value 4. Okay, well, we can do that, right? So 8 minus 2c equals 4, right? Our input is c, so we plug that into our function. and then we just solve. So I can subtract full 8 from both sides, and then I can divide by -2, and that's our value. And just as a check, C is in our interval. Okay, so that's a check. Wonderful. All right, so that's how we do it. Find the average value and then actually set those equal. So let me get you guys to try an example. Okay, so we're going to do the exact same thing where f of x equals x over 2, and then we're looking at the interval 0 to 6. Okay, so do the exact same thing that we did there. So go ahead and pause here. I'll jump to the solution. All right, hopefully you guys pause. Here we are. So I drew the picture. So we got this triangle here. The height is 3, excuse me. The base is 6. So the area is 9. Okay. Now plugging into our average value formula, we get a sixth times 9, which is 3 halves. Okay, so that's the first part. We got the average value of our function. Now, second part, we got to set the function equal to 3 halves and solve for c. Okay, so we get 3 there. We just multiply by 2 on both sides. And 3 is in our interval, right? This is the x value 3. So that is in our interval, and we're all set. Okay, let me get you guys to try um, one more here. Okay. So we're going to be learning, how to do more and more integrals and rely less on geometry as we go on. But let's just start with this. Okay, so let's say we know that integral of x squared from 0 to 3 is 9. Okay, so we've done the integral of x squared, but it was 0 to 2, right? So different area here. Okay, so we're going to assume that's true. Okay, again, later we're going to figure out how to actually calculate that. We're going to learn the shortcuts, right? But let's let's take it one step at a time. We're going to do the same thing here. So I know the integral is 9. Now we're going to do all the same stuff. Okay, find the average value and then find the c, right? So average value is easy because the integral is already done, right? So the average value is going to be 1 over 3 minus 0 times 9. So that's 3. Okay, so the average y value of x squared on the interval 0 to 3 is 3. Okay. Um, Now we're going to do the second part. We're going to do the second part. So f of c equals 3. Okay, but I know what the function is. It's x squared. So this is c squared equals 3. C equals plus minus root 3. Okay. However, check your interval. Positive root 3 is the only value in my interval. So really, c equals root 3 is our only c value. Okay. So now you go try one. Very similar, procedure here. So we're given that the integral from 0 to 3 of 2x squared minus 1 dx equals 15. Okay. Now I want you to find the average value and then find the c, where the function equals the average value. Okay, so go ahead and pause here. Okay, so let's go through this together. I know this is equal to 15, so my average value is going to be 1 over 3 minus 0 times the integral, so 15. So this is equal to 5. That's my average value. That's the first part done. Now I need to find f of c equals 5. Okay, so this is 2c squared minus 1 equals 5. So I can add 1 to both sides, divide by 2, and then again, my interval does not have negative root 3 inside of it, so I only get c as positive root 3. Okay, awesome. Okay, now we're gonna take our first step connecting integrals and antiderivatives. So this is a huge theorem. So this is called the whoa, big word, fundamental theorem of calculus. This is actually part one. Okay. So you know it's important because it has a name, and you know it's really important because it has like a pompous name, I guess. Fundamental theorem of calculus. Okay, right? So what's going on here? What this is saying is I have a function f of x which is continuous on a to b. Okay. Then we're going to define a new function, capital F of x. This should be hinting at 4.10, capital F of x. Then capital F of x is, whoops, is defined as capital F of x equals the integral from a not to b to x of f of t dt. Couple things going on here. So it's not a set in stone interval a to b. X is a variable, okay? So if you imagine, let me actually pause here and get you guys a visual. Okay. So ignore all this stuff on the left-hand side. All the specifics here don't matter. So what's going on here is uh, we have a function in red, and the integral tells us, this area in black, right? Now it's a positive function, right? So um, we don't have any of the net change stuff happening. So that we just want to simplify things to get a little bit closer to intuition, right? So this stuff is pretty hard, so there's not a lot of intuition going on here. So I'm trying to make it as simplified as possible for you guys. So the integral is, on these two bounds from left to right, right? Now, remember, we are not talking about a to b anymore. We're talking about a to some x value. That x is a variable. So what that is saying is, um, like for example, at this particular x value, I have a certain area, right? Um, then at this x value, I have a certain area. This x value, I have a certain area. And as x can go up or down or whatever, x is like my input. The area under the curve, right, is the output. Okay. Now I'm saying area here because this is a positive function. In reality, we were talking about the net change, right? Because we're doing the integral. But notice what's happening there. I have an input x and an output, which is the area slash, net change, blah, blah, blah. That's a function, right? Input x, output, not necessarily y, but we're getting an input and output. That's a function. So when we define this, we're defining it as capital F of x, okay? This is a function. We have an input x, and the output is whatever that area slash net change in area is, okay? So we're defining that's our capital F of x, okay? Well, so what, right? So what? Well, it turns out capital F of x is in fact an antiderivative of little f, okay? Then, this is the big guy, capital F prime equals f of x on a to b. Okay, so this is the connection. We have the integral, right? The area under the curve, or the net change in area under the curve. That actually results in an antiderivative. Okay, this is the antiderivative. Okay. This is the connection. Now, there will be a part two to this as well, but that'll help us evaluate integrals. But for now, this is what we got. Okay. So now, when we're doing antiderivatives, um, we have this, powerful tool. Now, what can we use this powerful tool on, right? What can we use this on? Well, let's look at an example. Okay. So let's look at g of x equals this integral from 1 to x of 1 over t cubed plus 1 dt. Okay. Now I want to find the derivative of g. I want to find the derivative of g. Okay, so notice what's happening here. Um, First of all, this is my inner function f of t. Okay. So in order to use the fundamental theorem of calculus part one, I need this to be a continuous function. Okay. Now this is discontinuous at -1. You can set the denominator equal to 0 and solve. You get -1 as a discontinuity, but that's not in our interval. We're doing 1 to x. So this is continuous. Okay. Um, this is continuous. Then what we know from the fundamental theorem of calculus, that conclusion, g prime of x is simply I plug x into that integrand, 1 over x cubed plus 1. Okay. So in some sense, the integral and the derivative just cancel, right? So I have an integral here. When I do the derivative, they just kind of disappear, and I have that inner function left over, 1 over x cubed plus 1. Okay. All right. So let me get you guys to try an example. An example. Uh, g of r here. So I'm switching the variable names around. It doesn't matter. Okay. Dx, that's okay. Okay. So verify the condition and then use the fundamental theorem of calculus, FTC part 1. Okay, hopefully you guys paused. So this function here, this is continuous. Check. Okay. So then if I want to take the derivative with respect to r of g of r, that's the derivative with respect to r. I'm spelling it out a little bit more here. It's okay if you didn't. Okay. So you can see what I mean. Essentially, the derivative and integral are going to cancel. And on the left, I'm left with g prime of r. On the right, I'm left with that inner function, but r, right? The variable I'm looking at inside of it. Okay, that's my derivative. Okay, let's get a little crazier. Let's get a little crazier. So let's do another example. Now we're going to be using chain rule. Okay, so in both these examples, it was just the variable x or r or whatever in the bounds. What if it's not? What if it's a function all on its own, right? So let's look at capital F of x equals the integral 1 to square root x sine of t dt. Okay. Now I want to find capital F prime of x. Okay. First step, that's continuous. Check. Now we can jump to the derivative. So f prime of x, capital F prime, excuse me. First step is the same. I just plug in my upper bound to that function. Okay. But we get chain rule. I have to multiply by the derivative of the inside. So this is x to the half. So I have to multiply by half x to the negative a half. Okay, so that's chain rule, derivative of the inside. I can bring those things to the denominator. Generally, when we're looking at answers, I don't want a mix of rational exponents and roots. I either want all rational exponents or all roots. Okay, so here I'm doing all roots. Okay, and that's our derivative using some chain rule. Now you try. Now you try. Let's look at this example. So capital F of x equals the integral 1 to x cubed cosine t dt. Okay. Now I want you to find capital F prime of x. Go ahead and pause the video and try it. All right. So what you should have got, first of all, the cosine is continuous, so we're good. This is going to equal cosine of x cubed plugged in there times 3x squared. Okay, so we write that 3x squared cosine x cubed. Okay, got that chain rule happening. Awesome. Okay, so now we've dealt with if when it's just the variable on its own. Now we've dealt with if it's other weirder functions, right? We gotta do chain rule. But we haven't touched functions in both bounds. We've only had a function in the upper bound. Okay. What if we have a function in both the upper and lower bounds? So let's look at this guy, x to 2x of t cubed dt. Okay. And I want f prime of x. We can use that integral splitting property. Okay. So I can rewrite capital F of x. So I'll just rewrite it here for a second. So we have all the steps laid out. So I can split this from 0 to 2x t cubed dt plus x to 0 t cubed dt. Okay. So see what I did there? It goes from x to 0 to 2x. Right? Kind of cut it in half there. Now I can reverse the bounds on the second integral. Remember, when you switch bounds, you pick up a minus sign. Okay. Now that I've done this, notice in both spots there, it's a function just in the upper bound, and we know how to do both those pieces. We know how to do both those pieces. So then f prime of x, this is going to be 2x plugged into t cubed, so it's 2x cubed, all cubed, times the derivative of 2x, which is just 2. Then minus, and then it's x plugged into the cube function. So that's just x cubed. So we can simplify. This is 16x cubed minus x cubed, which is 15x cubed. Okay, now you try. So let's do another example. So let's call capital F of x equal the integral x to x squared cosine t dt. And I want capital F prime of x. Okay, so go ahead and pause the video here. All right, let's do it. So we can do basically the exact same strategy we did earlier. So capital F prime of x, this is going to be the integral 0 to x squared cosine t dt plus the integral x to 0 cosine t dt. Then we can flip the bounds on the other one so that all of our function bounds are in the top. Okay. Now we can take the derivative. So f prime of x, this is going to be, so we plug in the bound, so cosine of x squared. Then we multiply by the derivative of the bound, 2x. Okay. Then we get minus, and then we get cosine of x times 1. Okay. So that's 2x cosine of x squared minus cosine of x. Okay. And then we cannot simplify that any further. Okay. Now, you could, once you get used to it, you could just start jumping, right? Notice here, it's always the upper bound, right? The x squared minus the lower bound with the x, okay? Um, you don't have to necessarily always do all that algebra, but I'm just showing you where it's coming from, right? Okay, so that's a whole lot of practice using the part one of the FTC. What's part two? Part two is actually what helps us evaluate integrals using the antiderivative or any antiderivative. Okay. What this says is, again, f is continuous, not ff. F is continuous. Okay. And capital F is any antiderivative of f of x. Then the integral, okay, this is how it's going to help us find integrals now. What we do is we plug in the bounds to the antiderivative. So I get capital F of B minus capital F of A. Okay. So what's our solving strategy going to be? what it's going to be is we're given an integral, right? Integral from a to b of f of x dx. We need to find an antiderivative of f of x, and then we'll plug in the bounds, right? Top bound minus bottom bound. Okay. Now we can use all that stuff we talked about in 4.10. Okay. So let's try it. So let's look at the integral -2 to 2 t squared minus 4. And we're really going to learn the notation here, how we write all this stuff, okay? And how we do it, carefully, but we don't make any algebra errors, things like that. So t squared minus 4. From 4.10, we actually know how to find the antiderivative of this, right? Remember our integral power rule. Okay, so just as a reminder, I'll put it in red here. So just as a reminder, kind of two things. If we're integrating a constant dt, that's kt plus c. Then if we're integrating t to the n dt, we add 1 to the power and divide by that new power plus c, right? So we can do that here. So this is going to equal, and we're actually going to put this in brackets. So when we're doing indefinite integrals, excuse me, finding the antiderivative, doing indefinite integrals, we didn't do the brackets. Because we have bounds here, we need brackets, and I'll explain why. So brackets, and then we're going to put in our antiderivative here. So t squared, if I add 1 to the power, that's t cubed, and then I need to divide by 3. Okay. Add 1 to the power and then divide or multiply by the reciprocal. Then minus 4, that is simply minus 4t. Okay. Now you might be asking, what about the plus c, right? What I'm gonna show you in a second is we actually don't need the plus c for definite integrals. Okay. Remember, I told you in 4.10, if you don't put you better put a plus c on indefinite integrals. Okay. You better put a plus c on indefinite integrals. I'm going to mark you down if you don't. For definite integrals, we don't need it. Okay. Now you might, maybe you forget. Maybe you forget, right? Maybe it's ingrained in your brain that you need to always put plus c, right? So let's put plus c, see what happens. Okay. So let's just try it. Remember, this works for any antiderivative. Okay. So we're going to learn why. Now we have brackets here, and we need to put our bounds on the right-hand side there. So this is denoting that we have an antiderivative, and then the next step we're going to do is plug in the bounds and subtract. Okay. So the next step, we do that. So I'm going to plug in 2. So I have 1/3 2 cubed minus 4 times 2 plus c. So notice there, this is all just the upper bound. I plugged in 2. Then I subtract, and now I'm going to plug in the lower bound, -2. Okay, so I got my -2's here. Okay, so just take a step back for a second, think about what we did. We found an antiderivative, that's like our capital F and the top of the screen there. Then we plugged in our bounds and we did top bound minus bottom bound. Okay. Now the rest is algebra or calculator work. So this is 8 divided by 3 minus 8 plus c. That's that first bit. Then I have minus, and then this is going to be -8 over 3 plus 8 plus c. Okay, now I can distribute that minus sign. So it's plus 8 over 3 minus 8 minus c. And check that out. The c's canceled. Okay, the c's are always going to cancel. So with definite integrals, we don't need to write them. Okay, it's not necessary. Technically, you could think of it as always being there, but it always cancels. Okay, however you want to think about it, we don't need to write it for definite integrals. Okay, this is so important that we're going to take a second and you're going to write this in your notes. Okay, uh, for indefinite integrals, don't forget plus c. For definite integrals, plus c uh, can be ignored. Okay, you do not need to include it. All right, so let's continue here. So this is 16 over 3 minus 16, which is negative. It's not negative 24 over 3. What is it? Negative 32 over 3. Okay, and that's our integral. That's our integral. Okay, awesome. And if you draw the picture, I'm going to do it pretty sloppily here. This is what our picture looks like from negative 2 to 2. So those are our bounds. So the integral we were finding was this guy here. So that's why I had a negative answer. It's got a negative area. Okay, so that's our integral. All right. Now you try this one. Now you try this one. Integral 1 to 9 x minus 1 over root x dx. Okay. So got to get used to doing power rule here. I will give you a hint because I don't want you guys to waste, too much of your time. What I want your first step to be is to split the fraction like this. Okay. Now you're going to rewrite those as x to some power and do the power rule, the integral power rule, right? We're doing integrals, and then do all the algebra. Okay. So go ahead and pause here and try as best you can on your own. If you hit a stopping point, that's okay. Okay. Let's see how you guys did. Let's try it. Okay. So we can rewrite this. So x over root x is root x. And then this is my, leave that. Now we can write those as x to some power. So this is x to the half minus x to the negative a half dx. Okay. Now, integral power rule, we are going to add one to the exponent. So this becomes 3 halves. And then we divide by 3 halves. Okay, so that's multiplying by 2/3. Same thing for this one. So the minus kind of carries along. Then x to the negative a half plus 1 is positive a half. Then we divide by that, 2 over 1. Okay, and now we have our bounds, 1 to 9. So we can plug in. So this is 2/3, 9 to the 3 halves, minus 2, 9 to the half. Okay, so I plugged in 9 everywhere. Then I'm going to plug in 1 everywhere and subtract that result. Okay. All right, all right, all right. So all of this is possible to do without your calculator. I would recommend trying it. Keep your algebra skills good. So I'll show you all the work. Of course, at any step you could jump in and do your calculator, okay? So this is 2/3. 9 to the 3 over 2. This over 2 is a square root, okay? So that 9 becomes a 3. The 9 and the square root becomes a 3, and I just got 3 cubed. Same thing here, 2, 9 to the half is it's just square root 9, which is 3. Okay. Then here, 1 to any power is 1, so we have those can just disappear. So this is 2/3 times 27, which is 2 times 9 is 18, minus 6. And then we can distribute the negative there. Okay, so this is 14 minus 2/3. If you get a common denominator there, that's 40 over 3. Okay. All right. Let me get you guys to try one more. This is the integral 1 to 2 x to the negative 4 dx. Okay. Really try to get as much practice as you can doing this power rule stuff. So pause here. Okay. Hopefully you paused. So we can get our antiderivative. So we add 1 to the power, so it's negative 3, and we divide by negative 3. Okay, and then we have our bounds. So now I can, so that's negative a third. I can plug in 2 everywhere. Okay, minus negative a third, 1 to the negative 3. Okay, so this is negative a third times 1/8, right? 2 to the negative 3. Negative, so it goes in the denominator. 3, so it's cubed, it becomes 8. Then the two negatives here cancel, be plus, and then just a third. The 1 to whatever is just 1. Okay, so this is negative 1 over 24 plus a third. Okay, and you get a common denominator, negative 1 over 24 plus 8 over 24, and this is 7 over 24. Awesome. Okay. Notice these are the shortcuts, right? We have no limit of a Riemann sum happening anywhere, right? Now, of course, this is all happening in the background. Just like with derivatives, that limit definition of a derivative is always happening in the background, but we just stopped looking at it eventually, um, so that we could, use the shortcuts, right? Same exact thing here. All right. Okay. So let's just look at one more thing very quickly. Um, So we're going to look at how far does Mr. Dong travel if, excuse me, in 5 seconds if his velocity of t is equal to 5 plus 2t, right, feet per second. How far do I travel? Okay, so this is getting at the idea of the total area where we take the absolute value. If I'm talking about how far do I travel, my total distance traveled, I don't want any um, distances like, canceling each other out or anything like that. So just let me try to tug at your intuition here for a second. Let's say I'm running, so I'm running this direction, and then I double back, and then I keep going, right? Um, so remember how we view moving to the right as positive and to the left as negative? This is kind of analogous to our area being positive above and negative below. So if we were simply to integrate our velocity, stuff is going to cancel here because some of it is positive, some of it is negative. I don't want that to happen. I want it to learn, I want to know how much distance I travel in total, which means I have to take into account all of the overlaps and things like that. So the way we fix it, we take the absolute value, just like we did with the area. So the way we fix the area, the negative and positive issue with the area is we took the absolute value, everything became positive, so nothing canceled with itself. Same exact thing here. So so total distance traveled equals your integral of the absolute value of the velocity. Okay, from, A to B or whatever. Okay. Okay. Now, in this case, for our problem, it's going to equal the integral from 0 to 5, right? We're talking about 5 seconds here. Absolute value 5 plus 2t dt. In this case, my velocity is always positive. This is a positive function. You can graph it on a graph or whatever you want to do, plug in values. This is already positive, so the absolute value does nothing. Okay, so in this case, the absolute value does nothing. And now we can integrate. Okay, so antiderivative of a constant like 5, that is simply 5t. Now, the 2t, the plus 2 hangs along, and then t, I add 1 to the exponent, which is 2, and I divide by the new exponent. Okay, so this is, I'm going to plug in 5, so I have 5 times 5 plus 5 squared. So the 2's cancel, which is kind of nice. Then minus 5 times 0 plus 0 squared. Okay, So all that's zero. We can ditch that. So I have 25 plus 25, 50 feet. Okay. So if my velocity is 5 plus 2t feet per second, for where t is like the time passing, then in 5 seconds, I will travel 50 feet. All right. That's the end of this video. Thank you guys for watching.